Hello everybody, welcome back to the Gregorius Maths video. And yeah, I'm just, I guess, continuing on with the theme of probabilistic inequalities. Last time we looked at the probability version of Cauchy-Schwarz. This time we're looking at the probability version of Jensen's inequality. And it pretty much immediately follows from like what I think is the standard version, although I hadn't really heard of it until I saw it this year, so maybe I could be wrong about that. So yeah, we're just going to be showing the normal version and then applying that to probability, and I'll include a little note at the end about one small little consequence, but I'll dedicate another video to maybe some cooler corollaries. Maybe even later today, but definitely by tomorrow. Anyway, let's get straight into it. So we need to deal with convex functions, and convex functions are functions in which the line joining 2 points on the curve is always above, so like this. The line joining these 2 points is above the curve, okay? All right, so that's what a convex function is, just as a recap. Now, okay, the theorem that I want to prove, or the lemma that I want to show before I state the actual probabilistic version of Jensen's inequality, is the following, and that is that for any convex function f, it is the supremum of all of the lines that lie below it. Okay, so if you take all of the lines that lie below, completely below my function, then, and you just take the pointwise supremum everywhere, you get f, right? So how do we put this in more concrete terms? What we really want to show is that for a convex function f, for all m, there exists some a and b such that f of m is equal to am plus b, and f of x is strictly greater than ax plus b for all x. Okay, so what I'm claiming is that for every single m that I choose, there will be some line, so there'll be some a and b, and so that I can write f of m is exactly equal to am plus b, as in, you know, it's tangent, or, you know, f of m lies on my line, but f of x, my convex function, is always above the line for all x. Okay, right, so now we have a more sort of concrete statement to work with. Let's get busy and prove it. Proof. Okay, so we've picked some m, so let's let m lie between some x and y, so x is less than m, and that's less than y. Then, by the intermediate value theorem, m must be on some point along the line just joining x and y, right? If you have a straight line joining x and y, it must hit a value of m somewhere along there. So in other words, there exists some t between 0 and 1 such that m is equal to tx plus 1 minus ty, right? Because this is the parametric form of the line joining x and y. You can see at t equals 0, you just get y, and at t equals 1, you just get x, okay? And another way that we can rewrite this inequality, this equality, is if we write m as tm plus 1 minus tm, then we get that this is just implying that t times by m minus x is equal to 1 minus t times by y minus m. This will be an important equality later, so I'm just keeping that there for now. All right, now, back to the matter at hand. By the fact that our function f is convex, we have that f of m, which is equal to f of tx plus 1 minus ty, well, this must always be below the line adjoining x and y, so it must be less than or equal to the line joining f of x and f of y. So it must be less than or equal to t f of x plus 1 minus t f of y. All right. Now, again, if we do our similar trick of writing f of m as t f of m plus 1 minus t f of m, then this implies that t times by f of m minus f of x is less than or equal to 1 minus t times by f of y minus f of m. Okay. Now, we're going to multiply both sides by by m minus x. So this gives us that t times by m minus x times by f of m minus f of x is less than or equal to 1 minus t times by m minus x times by f of y minus f of m. And the reason why the sign doesn't change is because m is bigger than x by assumption. Now we plug in our inequality here. So this gives us that 1 minus t times by y minus m times by this thing is less than or equal to that. Well, we can again cancel out the 1 minus t on both sides with the assurance that it's not negative. And also it's not 1 since m is not exactly equal to that. So we can just cancel it out without any fear of dividing by 0 or flipping the sign. So this gives us that y minus m times by f of m minus f of x is less than or equal to m minus x times by f of y minus f of m. And then let's rearrange this so that we get that f of m minus f of x all over m minus x is less than or equal to f of y minus f of m all over y minus m, like so. Okay, so we've done a bit of algebra. And, whoops, and what have we obtained? Well, we've obtained that the slope at x is less than the slope at y, because m was an arbitrary choice. And this holds for all m's, so yeah, so the slope at x is less than the slope at y. And so what we're going to do is we're going to let a be the supremum over all z less than x of all of these slopes, okay? Of f of m minus f of x all over m minus x. Okay, so it's the supremum of all the slopes. It's the least upper bound of the set of all of these slopes. And this implies that, well, it must be bigger than this, or at least bigger than or equal to this, since it's an upper bound. But it also must be, it's a least upper bound, so it must be less than this, right? So what we get is that f of m minus f of x over m minus x is less than or equal to a, but that's also less than or equal to f of y minus f of m all over y minus m, like so. Okay, now, what are we doing? So first things first, let's go case by case here. If z is less than n, is less than m, right, then this means that f of m minus f of z over m minus z is less than or equal to a, right? Because we use this side of the equality since x is less than m, so we're using this side. And if we rearrange this, what do we get? We just get that minus f of z is less than or equal to a times by m minus z minus f of m. And this implies that f of z is greater than or equal to, just flipping the sign here, a times by z minus m plus f of m. And in case number 2, in which z is bigger than m, then we use this side of the inequality to get that a is less than or equal to f of z minus f of m all over z minus m. And this implies that a times by z minus m plus f of m is again less than or equal to f of z. So we have a candidate for our function, we have a candidate for our real numbers a and b. Namely, so we have a candidate for our numbers a and b. Namely, if you just consider the line given by f of z equals to az minus, plus f of m minus am. So just this line here. What do we have? Well, we know that when z is bigger than m, f of z is greater than our line, which is what we want. We also know that when z is less than m, it's bigger than our line. That's good. And what about when z is equal to m? Well, f of m is just am plus f of m minus am, so you just get f of m, which is exactly what we wanted. So we have found real numbers a and b such that both of these conditions are satisfied, and so our statement is true. Okay, good. Now, what on earth does this have to do with probability at all? Well, what I want to do now is to consider the very special case when m is equal to the expected value of some random variable x. Okay. Let m equal to the expected value of x. Then, what do we have? If we apply our theorem to this case, firstly we have that f of x is bigger than or equal to a times by x plus b. So there's some real numbers a and b for which this is true. And now if we take expectations on both sides, then the expected value of f of x is greater than or equal to a times by the expected value of x plus b. But that's just equal to, since m is the expected value of x, that's just equal to f of e of x. So what do we get? I'll write it in a different color. This implies Jensen's inequality, but the probabilistic version, which is that for a convex function f, we have that the expected value of f of x is greater than or equal to f of the expected value of x, like so. And one comment that I just wanted to make is that this guarantees that the variance is always positive, because x squared, f of x equals x squared, is a convex function, and so we're allowed to apply it here. And so we get that the expected value of x squared is always greater than the expected value of x squared. And so the variation, which is just the difference between the two, will always be greater than or equal to 0. And so yeah, that is Jensen's inequality proven. As I say, I will make a video on the consequences, or a couple of the consequences of this probabilistic version. But yeah, hopefully you found that somewhat satisfying, and I'll see you soon. Ta.